Following on from the previous video, we started out with this limit here. We started out with this, and then we took the natural log of the whole thing. So take the natural log of the whole thing. That then gave us this. Okay, and then from here, and then from here, we would then translate this into this. And the way we did that was by looking at this. Rewrite this 1 over n as delta x. So rewrite the 1 over n as delta x. And then this thing here, basically we would then translate this thing into this thing here. And by translate, we mean that we're gonna keep everything the same. We're gonna preserve the true meaning of it, but just rewrite it in a different form. So everything, the true meaning of this thing here will be the same as this, but then we are just rewriting it in a different way. Okay, so we would then translate this into this. Okay, so what you've got here is really this block times this block here. You don't actually need the square brackets here. You don't actually need this, because what you've got here is really this times this. But the thing is, we want to visualize the square brackets. So visualize the square brackets. Okay, so hang on. So at the moment, really, you've got this thing times this thing here, but visualize the square brackets. So visualize it as this. Okay, so now you've got this. So here you've got one thing multiplying with another thing, but visualize this block here as one block. But then in this block here, here's just a trick. Here's just a trick. In this block here, get this and then take away 0. That's the trick that we're going to use. So from here, so this here is this thing here, but then we are rewriting this block here as this thing, which is this thing here, take away 0. So really this whole thing here is this thing here. Okay, so we are rewriting this thing as this thing take away 0. Okay, so now we started out with this. We started out with this, and then we would translate it to this. And then the next trick is to rewrite this block here as the block take away 0. Okay, but so the reason why we started out with this, the reason why we are changing it to this form here, we are preserving everything. We are preserving the true meaning of it, but we are just rewriting this in a different form. So now that you're in this form here, you should notice. Well, you have to train yourself to notice that. Look at this, original, and then this here is original plus a tiny amount. Okay, so and then you divide. Well, you've got to take the limit of delta x as it heads towards 0. So you've got to train yourself to be able to recognize this thing here. This thing here has some sort of meaning associated to it. Look at this here. Hang on, original, and then original plus a tiny bit. So remember something like this, something in the past. F of x plus a tiny bit. In the past we would use h, or sometimes we would use the h as delta x here. So look at this here. F of original plus a tiny bit. Take away the original here. Take away the original, and then divided by the tiny amount, and then take the limit as that tiny amount tends to 0. So while looking at this here, you have to train yourself to be able to spot. There is a similarity between this and this here. Well, hang on. Looking at this here, you've got the original, and then original plus a tiny bit, and then divided by delta x, and then the delta x tends to 0. Hopefully, you've got to train yourself to be able to recognize this. But anyway, looking at this here, if I were to ask you, look at the hang on, but remember this. We're going to come back to this later. Okay, if I were to ask you, find the derivative of the natural log of x at x equals 1, you would then set up 2 points. You would then set up 2 points, A and B here, and then you would say, oh, the the average gradient that exists between A and B. Well, the average gradient that exists between A and B is given by this, because delta y here, this here is delta y. So delta means a small change in in our case here, it means a small change in y, and delta x means a small change in x. Sometimes we would use h to represent this, and sometimes we would use delta x. Okay, well, the average gradient that exists between A and B is given by delta y divided by delta x. So you would then say, this delta y here is given by this, take away this, and then the average gradient that exists between A and B is given by this. And then if you were to take the limit as the limit of this thing here as delta x tends to 0, then that would then give you the true gradient, and the true gradient would be this. And notice that this thing here is the same as this thing here. So when you were here, you have to train yourself to recognize that this thing here is really the derivative of the natural log of x evaluated at x equals 1. So hang on. So this thing, hang on. So we started out with this. Okay, we started out with this. Take the natural log of the whole thing. That would then give you this. Okay, and then slowly we would then slowly transform this into something that we would recognize. And then when you get to this stage here, you have to train yourself in the future to be able to recognize that this here is really the derivative of the natural log of x evaluated at x equals 1. Because look at this. Okay, well anyway, when you get to this stage here, realize that this thing here is you doing this, is you working out the derivative at x equal is you working out the derivative of the natural log of x evaluated at x equals 1. So that, anyway, that thing there is the derivative of the natural log of x evaluated at x equals 1, which is, hang on, when you put this into here, it becomes 1. Okay, so what we're saying is that when you take the natural log of this thing here, when you take the natural log of this thing here, it will give you 1. Okay, so we started out with this thing here. Take the natural log of this whole thing here, it will give you 1. So what we've got here is the natural log of this whole thing here. This whole thing here is, by the way, it is this bubble here. Let's imagine this as being that thing there. Hang on. So imagine this as being this. Okay, so we started out with this thing here. Take the natural log of this. This will then give us 1. Okay, so here you've got natural log of something equals 1. Natural log of something equals 1. So now exponentiate both sides. So that would then when you're here, e to both sides, e equally to both sides. That would then give you this on this side. It will give you this on this side. Okay, now these two will cancel out, giving you this thing here. And then on this side, e to the power of 1 is just e. So really what you've got here is e is this bubble here. And don't forget that bubble here is this thing here. So remember, so that bubble there, remember that bubble there is this thing here, 1 plus 1 over n to the power of n as n tends to infinity. So if you carry through here, what you've got here is e equals that thing there. So hang on. So looking at this, we started out with this natural log both sides. That will then give you 1. And then whenever you have the natural log of something equals 1, then you can exponentiate both sides. That will then give you this, and then exponentiate 1. That's just simply e itself. You see, when you have the natural log of something equals 1, these two cancel out, giving you the definition of e, giving you the true value of e here. So hang on. So if you really want to discover e for yourself, well, if you want to discover E for yourself, find something when you log it. If you want to discover E for yourself, or invent something that will allow you to find out what E is, find something that when you put it into here, if you log it, it gives you 1. Then that's how you can find E. If you can search for something that when you log it, it gives you 1, then you can just exponentiate both sides. Then these should cancel out, giving you the bubble equals E to the power of 1, which is just E. So if you want to find E, if you want to find a way of finding out E, then search for something that when you log it, it gives you 1. Okay?